everybody. Welcome on the presentation of your project. First, I will present to you the jury, which consists out of 6 people. In the first place, we have Mark Grauet. He is CAD master, as we can say, so he knows everything about CATIA in your design. The second place we have...
the second person is Mr. Wim Hageman. He's head of the Department of Industrial Technology and Sciences here at the KVO.
On the third place, the third person is Ronald de Vever. He is head of this department, not this department, but this facility.
The fourth person is Rob Baron. You may have seen him this week. He's the safety coordinator of the VLOC.
And then the fifth person is Alexander from Ostend, who has helped you with your design this week.
And the sixth person is William van den Hout, also as same as Alexander, he helped the teams out with some guidance and briefings.
So, the first team is Group 1. They may present their project as first.
Alright, so good afternoon everybody. We are Team 1. First of all, I'd like to really thanks a lot the EuroAvia team of Ostend for this symposium. It was a very incredible, very nice, very interesting experience for us, and we had a really good time here. It's already done. It was too fast. So let me introduce a little bit how we managed to create our flying wing. It was the first conclusion. It was really difficult to do all these things in 1 week, especially for us. For a lot of us, it was the first time we had to design and to come from nothing to make a flying airplane. That was difficult. So we start with a little slide. First of all, we will just introduce a little bit about aerodynamics consideration and how we choose the shape and the profile, things like that. And I will let one of the aerodynamicians talk.
So we had 3 different airfoils, because in the middle, in the root of the plane, we need a little more extremely thick airfoils so that everything can fit in all the equipment inside. So there's the GOE 500. And at the end, at the tips, we don't need that. We need a thinner airfoil, so we choose another one. But we couldn't make the transition from this tip to this thin airfoil just like that, so we have also in the middle another third airfoil. After a calculation, we found out that the wing area is supposed to be, as you see, 0.83 meters squared. It's found that according to in horizontal slide, when we knew the weight, and with weight we calculated, and the CL we calculated how much wing area we need. So the root chord is 500 millimeters and the tip chord is 140 millimeters. We have the aspect ratio of 10.3. We have sweep angle of 25 degrees to improve roll stability, and also by the sweep angle we get the control surfaces to be more further from the center of mass, so the torque they produce is higher. And also we have a twist angle, so that we have negative lift on the tips that will stabilize, that will provide longitudinal stability. So also that tips, this sweep angle make those tips away from central gravity, so so you get a bigger torque. These are the profiles we used. It's a little bad picture now, but because of the lighting. But here you can see the coefficients of pressure. And at the end we have the whole link. And there was some problem with we used XLR program for calculating. There was some problem with convergence, but at the end we got it.
Here's the equipment and the different devices you have to put into the plane, and therefore maybe Gunnar can do that.
Yeah, I'm gonna give just a short overview why we choose which device. So we choose the GoPro HD digital camera because of its high resolution and relatively low weight, and it is quite strong. In case we have to do some night missions, we also choose an infrared camera, the Photon IR, which is also used for different other UAVs, and yeah, it is really small. We needed to have an input-output system for the IR cam. It wasn't integrated, so we added it. Yeah, we also needed a pitot tube, radio receiver, GPS navigation system, which is really good because so we could control the UAV during the entire flight and also use autopilot systems. Servos, cables, of course, and due to safety reasons, we added a parachute recovery system. In case there is an electrical failure, we can eject the parachute and are able to recover our UAV. For propulsion, I think Jakob.
For propulsion, first of all, we approximate our total weight. It was about 10 kilos, and we use my model hobby experience that if you have total weight about 10 kilograms, you need about 3 kilos static thrust, and we choose Chechen production engine, which has 800 watts power. For this model, we use propeller 12 per 6 inches. It calculates us. We estimated this all kits through our free program, which is Drive Calculator. It's free. You can download it for free. And when we know how big is the current, we choose the biggest batteries, which are 5,000 mAh, and we calculate how much of these batteries, how many of these batteries we need to for our whole flight.
Yes, because here is a place where we have to bottle one of our first and biggest problems, the autonomy of the battery. So we made the first calculation with the idea of a mission of 2 hours, so a flight of maybe 2 hours and a half for landing and takeoff. And with the first calcul, we see that at the beginning we wanted an aircraft that was less than 5 kilo. And with the first calcul, we saw that we need, I think it was like 13 kilos of battery to fly 2 hours. So we had to find a solution. We spent a lot of time about searching maybe for solar cells, things like that, but it's not easy in our case because we don't have a big surface, less than 1 square meter, so we cannot have a lot of energy back. And finally, we choose the solution to make the mission in 2 legs, because Ostend is situated more or less at the half of the coast, of the Belgian coast. So we have the idea to make a first leg, for example, to the north, where going back can change the battery and make the movement. So we calculated the battery for 1 hour of flight. Next, please. Here you have an idea of the weights of the different equipment. The payload, the equipment, we know the exact weight because of the shells we did. But for example, the structure is an estimation because we haven't time enough to make to be sure of how the structure. We have an idea, we have an idea about how.
We've done calculation of that.
Yeah, we've done the calculation, so it's quite a good estimation, and we arrive at a plane of 8 kilo, 8.6 kilo, and the price, our most normal estimation is just to give an idea. Next, please. And here's the overview of the system. Maybe I can introduce it.
So there's everything what we need to control our model. Here is the receiver, CPU, which are given all of the parameters of the flight, and we can use also autopilot, which use GPS to control our mission. It's all.
Yeah, so just to give an idea of the utilization. Then here we arrive in the how we're going to set the equipment into the plane, but this is just it's not finished yet. We were busy with that, and time was running on, and so there is lots of missing. But you have the most important, the engine, and here those two ones are the camera, the HD camera, and the infrared camera. And we had time to show you this, but we had the idea to put the batteries, that's it, into the wings to have a good balance and repetition of the weight, and also an easy access to change it. And here you will have a few words about the structure and the structure.
I'm Richard. I work with Stefano, another guy. We work almost on structure and optimization for the weight of the structure, and also with a little bit of flight mechanics in order to make the airplane stabilized. So we were almost the connection team from the propulsion to the aerodynamicists that made very lot of work. We were discussing the possibility to storage, as Peter said, the batteries a little bit inside the wing, because the wing is wet. It goes from, as the aerodynamics says, from a big airfoil to two thinner ones. So we have the possibility to store a little bit of batteries into the wings in order to put forward the center of gravity and increase also stability. We done also a little bit of calculation about the structural mechanics and the resistance of the structures. We thought about the central part in epoxy resin with fiberglass, in order to don't avoid radio controller possibility, and have airfoils in carbon fiber in order to reduce weight. We thought that the worst condition was here, and we designed the point of contact between the two airfoils with the red formula for stress, and we found that the worst condition is not proportional of the surface, but the deflection in this length. And we found a value of sigma of 14 newtons, so our initial prediction to use thickness of the airfoil of only 1.5 millimeter is okay, is respected. Also with at torsional and flexional resistance. So we've done, as Peter said at the beginning, an initial idea of the weight and the structure, and then try to optimize it. That's all.
So here's about the wing. Now about the mission, we thought a little bit about it, but like everything, we will not run out of time. We had the idea to use a catapult for the takeoff, so we can reduce the weight and the size of the engine if we use the catapult, and for the landing, just normally on the belly, not on grass, on the sun maybe. Normally with 8 kilo, it should be about the control of the airplane. Normally the flights should be autonomous, without any human control during the flight, but it's possible to, in case of emergency, to give some order to the plane. And so in the installation, there is a control system, an autopilot, a kind of autopilot, but it's also the possibility to take the control from the ground. And there is also, as you said, parachute in case of any emergency or loss of power, or in this case, if it's needed not to break the plane. Did I forget anything?
Yeah, we forget another thing, and is that for flight mechanic stability and also for reduce the weight, we decided to use electroactive polymers in order to bend the last part of the surface. So we can use these cables that are a resistance of 15 newtons for each cables, and put some of these cables on this latter part of the airfoil and control them using different current. If the current is positive, the last part of the surface will bend like this. If the current is negative, it will be in the opposite, and the motion of this airfoil is proportional to the current, so we can control them.
I try to think if we talk about everything. Normally the structure, the shape we choose is stable. We know that because after our first approximation, as you said, we made the first prototype. We made this prototype first with winglets because we were unsure that there were enough EO stability. But after an estimation, we saw that not so useful, so we removed it. And the first one was not that stable. It was not too bad, but it's just kind of figure it when flying. So we decided to increase the angle of the sweep from 20 to 25, and then we did the other model that are more stable. Then we checked if this first approximation was right with the, as you said, the software, the aerodynamic software, that confirmed the number of stability. Did I forget anything? Okay.
Flight.
That's pilot.
You can try, but you give me 3 chances because everything is planned on the film.
Wow.
Well, wait, one more time.
No, but we do, when the second group is done, we will do a small competition again. Okay, the other group will do one flight, and then at the end, both we put a table here, and then you can have 2 chances again to compete and to beat each other. So you're not done yet.
So now, if you have any questions, we will try to answer the best as we can, but there is a lot of different aspects that we have ideas about it, but we don't really have time to go further in it, so we'll see.
What's the operating voltage for the motor?
It's 19 volts. 19 volts.
19.
19. And you have a battery capacity of 42 ampere hours.
Yeah.
Total capacity?
42. Current is 42.
It's an engine of 800 watts.
Yeah, exactly.
Maximum.
Maximum.
Because maximum. So
We were flying at 56% of the maximum engine power.
At how much?
56% for cruise flight.
Let's say 400 watts
Yeah.
divided by 20 volts means
No, 20, yeah.
90 means 20 amperes.
20%.
And you have 42 ampere hours.
Yeah,
So,
it's maximum current.
so you can fly during theoretical.
Sorry?
You can fly during
2 hours?
2 hours. 2 hours.
So we try to be pessimist with our calculations.
About the propulsion, I saw in the diagram of the schematics of the good beat system, the motor and how is it controlled?
Through electric controls, electronic controls.
In your weight calculation, is this one included or not?
Yeah.
the ESC, the speed control for the air.
Can you go back to the slide of the weight calculation? So there is mentioned the ESC at the bottom, and then you go to the slide with the weight calculation. Somewhere in the beginning.
The regulator included is included in the navigation system.
Motor controller and navigation system.
Good try.
So could you repeat the question, please? Could you repeat
So,
because we can hear.
At the last part, the propulsion is the motor mentioned, 320 grams.
Yeah.
But the motor needs a speed controller.
Yeah.
Is this included in the 320 grams?
Yeah, okay. Okay, I can say it because we forgot to take it for our presentation. But we chose some regulators, some electronic speed controller.
Mm-hmm.
It's YATI. It's the company which made this controllers is YATI, and the weight is about 50 grams.
But I think it's included in the total weight.
Yes.
We forgot to put it in here, but it's included in the total weight.
Because we put up usually to calculate the total weight using Excel files, and when we have to modify one thing, there were functions that goes to modify everything.
Oh.
Yeah.
I see a radio receiver of 22 grams. What will be the receiving distance for that target?
33 kilometers. This one? The range of the radio receiver, 33 kilometers maybe? I'm not sure.
Not in this moment. We found
how far we can
Normal regular civil range is about 2 kilometers, but we don't use it to contact with our transmitter. We use here in the navigation system. We use some modules which we are connected with our ground system.
So you have a ground system also?
Yeah. Because we have cameras and we have to send the pictures.
And what will be what is the output power of the ground transmitter?
Sorry?
What is the output power of the transmitter on the ground?
I don't know. We don't know. We just make it.
It's very important because we want to travel the coast.
We are not a specialist for this department.
There is a question at the back. Yeah. Yes, go.
I have just 3 questions. First of all, the polymer idea with electricity is good, but I would like to know how much weight does it add, how much electricity does it consume, and how structural safe is maybe that polymer.
Okay.
I will ask all the 3
I
questions.
can answer for your question.
Yeah, but I'll give them all and then
Okay.
the second, I'm not sure why there is a particle recovery system, because it's a plane that is going on the sea. No particles will happen if it has to land on the and the other problem is that it can land on the bed. So what did you include? And the third question, I just lost it.
Okay. I will start with the simplest, the parachute recovery system. When you land, you will not land on you will not land only on a boat, but you could also land on the seaside first. So there's some space that you will patrol upon the earth, so you can fall on people. So you need a parachute for this first reason. Another reason is when you have an impact from an airplane to the water, the energy of the impact is due to the differences between the density of the airplane and density of the ground. If you have a water, you have a less density than on the ground, but you have still a density, so you will have a crash. We don't to have a crash and destroy our 3,000 euro airplane. We want to save it. So this is the reason why for the parachute.
No, I was just asking, we can do
Okay. We don't have to burn money. And about the electroactive polymer, we add almost no weight and reduce some weight from about cylinder, 70 grams. We don't do that for reduced weight, but also for have to be lighter. To be lighter as possible and to control the surfaces without many servos, because we want to avoid instability of we want to be able to move smoothly and with as less weight as possible on the wings. The weight of an electroactive polymer is proportional to the number of wires that we add on the surface. The number of the surface of the wires depends on the aerodynamical loads on the control surface. An electroactive polymer can do attraction force of 15 Newton. So at low Reynolds number, you will not have to move 15 Newton on your surface of control. So we estimate to have 40 Newtons for all the moving parts, so we can do 40 newtons divided 50 newtons to obtain the number of wires that we need. And the power needed by these wires can be given by our batteries, because in our cruise condition we use only the 56% of the power of the engine. So the power that is not going through the engine can go through these materials and control them. They need something like 15-20 volts, so they don't need so much battery. They don't give so much battery consumption. So we can lose a little bit of our batteries to avoid weight and to be lighter again.
Any other questions?
Was there a big difference, or was there a difference between the center of gravity you calculated and the final center of gravity on your foam model? So you did simulation of your airplane stability, and that showed you, or you decided on the center of gravity. Then you made the foam model. So my question is,
we are not so close. Our calculations are done using some assumption. They are not really correct.
okay.
For example,
So you don't know?
no, we more or less we know, but we have to do some assumption. These assumptions.
You know, in an airplane, more or less means PID. PID is pilot is dead. So,
Well, I'll show you the only assumption that we cannot that we do.
no, it's okay.
We have no inner structure. We don't have to calculate the center of gravity due to the presence of an inner structure to all batteries.
Yeah, but I'm not talking about the mass center of gravity as a result of the calculation. I'm talking about the center of gravity decides to have stability and balance in your aircraft. That's what I was talking about.
On this one or in the one?
Well, on the one you calculate and on the one you fly.
Yes, this one we calculate. We do assumption like mass. If the mass is here, each center of gravity is here, so another mass is there, each center of gravity is there, and make resultants of the forces and find in this way using a piece of paper and more or less with also assuming a constant thickness of the foil in order to approximate it.
So that center of gravity you obtain the position, so it also reflects the payload you have in the fuselage and so on.
More or less.
Thank you for your attention.
Okay.